like runner-ups. The second lecture was about matrix models, which is a very, let's say, transparent way of trying to work with quantum spacetimes, quantum gravity, at least in 2 or more dimensions. So it was the second lecture, and the third lecture will be about black holes. And I believe black holes are a good window to the world of quantum gravity, because basically for quantum gravity to be relevant, you need something that is both small and massive, or at least very, very dense. One of the options was the beginning of the universe, when everything was very compact and energetic. But it's quite difficult to basically test anything about the earliest moments of our universe. Like you can do something like derive the effects of inflation or something from cosmic microwave background, but it's very difficult. And there's a lot we don't know what is going on in there. Now, it's different with black holes. There is a different issue with black holes. That's the best way to put it. Because black holes are still present. We have been able to make a picture of a black hole, and it is probably safe to assume that in the next couple of decades, we'll get to know black holes very well. Now, the issue is that the effects of quantum gravity probably are not so important outside of a black hole, but only inside. But I'll try to show that even the things that are happening inside the black hole can be affecting physics outside. So that's why I think black holes are a good window into this regime of physics, despite black hole being not a good window into anything, because basically they capture every signal we try to send towards the direction. Now, for those of you who don't know, this is the anatomy of a black hole. So black hole is an object that is so massive or so dense that not even light can escape it. And the anatomy is basically that all of the mass is collapsed in a single point that we call the singularity. And there is a region a couple of kilometers away from the singularity that is called the even horizon. And basically this is the point that not even light can escape. So this is like the boundary between the rest of the universe and the interior of a black hole. Now we know that the situation can be more complicated. So for example, if you have a rotating black hole, then the singularity isn't a point, it's a circle. So you can have different effects, and the even horizon isn't a perfect sphere, as in this case, but it's basically a rotational ellipsoid. But the basic idea is still the same, like all of the mass is deep inside, and then there is a boundary that you cannot escape. This is the relation between the mass and the size of the black hole. So size, this is the radius r, and this is the mass m. This relation, basically, the important thing is that it's linear. So the radius grows linearly with the mass. And basically, if you set the units g and c to 1, so it's just basically r equals 2m. So that's a very useful shorthand for this. Now, what is actually going on is that when you place a lot of matter and it collapses into a black hole, it means that basically there is an infinite curvature in a space-time. So Einstein formulated the theory of gravity as a theory of curved space-time, and basically the matter is producing the curvature, and then in the curved space-time, geodesics are, well, different than straight lines. So basically, to describe a curved space-time, you need something like a Pythagorean theorem, something to measure distances. And during the first lecture, I showed that basically the metric tensor, which is used to measure distances in 4-dimensional space-time, is a 4x4 matrix, or a 4x4 tensor. In the case of Schwarzschild black hole, the situation is rather simple, because most of the 16 elements in this tensor that you can use to measure distances in the space-time around a black hole are zeros. You only have diagonal elements, so only 4 of them, and basically 2 of them are the same as in the flat empty space. No, flat, not just empty, but flat space. And well, 2 of them look the same. It's basically the first element is this. The second element is 1 over this. And this element basically tells you that if you have somebody sitting here very close to the event horizon or somewhere close to the horizon, that how does the time moves with respect to a very distant observer. So if you are sitting very far away from the black hole and you see someone falling down the black hole, then this expression tells you how are the watches on his wrist slowed down. And you can see that when you plug in the distance r equals rh, so the horizon value, then this is -1 + 1, so it's 0. So you basically see the time being frozen for the person falling down the black hole. So this is the basic situation with black holes. You have this special boundary, singularity, and then some prescription about the flow of time, if you want to put it like this. Now, Stephen Hawking is famous for many things. And one of the things he's probably the most famous for is called the Hawking temperature. So I'll try to now discuss how he realized that actually black holes do have some temperature. And it began with something called an area law. So basically Hawking was playing with different types of black hole solutions, and he realized that no matter what you do to the black hole, the surface area can only increase. So a trivial example is that if you take a stone and you throw the stone inside a black hole, mass of the black hole will increase, and so will the radius and therefore also the area. So this is a very trivial statement. If you add a mass to a black hole, its surface will increase. Now this is less trivial in the case of a rotating black hole, because you can throw something inside a rotating black hole in a way that it will slow down the rotation, and you can actually extract part of the rotational energy. So it's not as trivial as it seems, that the area can only increase in those cases. And the least trivial example is basically black hole merger. So you can have 2 black holes, each of which has some surface area. And when they merge together, they will radiate gravitational waves. This causes them to lose some portion of their energy and also therefore their mass. So for example, if you have 2 black holes, one has 30 solar masses, second have 20, then the resulting black hole after merger won't have 50 solar masses, but will have something like 40 or 45, or depending on the details of the merger. But the bottom line is that no matter how will they collide and merge, the resulting area will be larger. This is an important point. So Hawking coined this an area law. So basically, no matter what you do with a black hole, its area can only increase. And it's an interesting observation, because it's a unique one. Most of the things we know in physics don't behave this way. You can increase them, you can decrease them. For example, energy. Energy can go up and down, velocity up or down. But this seems that this property is basically only growing. And this has been just proven theoretically by Hawking, but it has been tested recently. And by tested, I mean some folks computed from gravitational waves what was the area of the black holes before merger, after merger, and they show that, okay, in this one experiment or observation, Hawking area law was satisfied. But still, okay, so it seems to be working, but people believed this a long time ago. And somebody called Jacob Bekenstein realized that, well, okay, this looks familiar. We also have another rule, another physical variable that can only increase, which is the entropy. So Hawking realized, okay, and the surface area of a black hole can only increase. And then Bekenstein was like, okay, also entropy can only increase. So is there something more to it? Is there a relation between the area of a black hole and a surface of something and an entropy of something? And he started working on this problem, and he basically did a lot of tests. And again, I mean tests in a theoretical sense of the word. So, for example, he asked the following question. If I lower one bit of information into a black hole, what does happen to its surface area? Well, why information? Well, because we know that entropy is basically the measure of missing information. We know it as the measure of disorderedness of the system, but it basically also can be stated as measure of how much information you don't know about the system. So when the system is in an ordered state, every spin is up. You need very little information to know everything about the system. I just told you in a single sentence, every spin is up. If every spin is pointed randomly, then you are missing a lot of information about the system because I have to spell out the orientation of every single spin to describe the system. So entropy is the measure of missing information, and Bekenstein was playing with the equation and trying to figure out what happens if you drop one bit of information into a black hole. What does it mean, one bit of an information? So for example, it can be a two-state system that can either be in a ground state or in an excited state. Or it can be an oscillator that can be in ground state or first excited states or something like this. So he tried to figure out, well, okay, what is the simplest way I can do a physical manifestation of a single bit? And then what happens when I try to drop this single bit into a black hole? And what he realized is that the black hole area has to increase by a fixed amount. And using this simple calculation, he basically showed that what is the total information that you can store inside a black hole. So for example, you start with the smallest possible black hole, and then you just start dropping bits inside and see what happens with the black hole. And he basically found out that there is a relation between the total entropy of the black hole and its surface area. And this is the relation. So it's the entropy equals Boltzmann constant times the surface area divided by 4 times Planck's area. Planck's area is just Planck's scale, Planck's length squared. So basically what he did is he said that, okay, when you are trying to write the fundamental law of thermodynamics, you have to consider also increase in entropy of a black hole. So we know that if you have an isolated system, the entropy can only go up, but now it's entropy of the system plus the entropy of a black hole, which is its surface area. So this was, I would say, among the most important results in theoretical physics during the last century. This very deep realization that first, black holes do have entropy, and it's proportional to the area divided by Planck's area, and not the volume as we would expect naively. Why is it weird that black holes do have entropy? It's because, well, entropy is the measure of missing information, but in Einstein theory of relativity, there is not much you don't know about the black hole. When you put together enough mass to form a black hole, it will collapse into a single point, and basically the entire thing is described by three numbers: the total mass, the total angular momentum, and the total charge. So we're used to be describing black holes only using three numbers, and now Bekenstein showed us that, well, there seems to be a lot you don't know about black holes. So you're using just three numbers, but there is something going on in there. There is some kind of disorderedness inside. Or it's not clear whether this is inside or whether the entropy is stored at the horizon, but somewhere it is. Okay, so back to Hawking. So first Hawking derived the area law, then Bekenstein figured out the exact relation between the entropy and the surface area. And now Hawking again was thinking, okay, black holes do have entropy, so that means they probably should have also some kind of notion of the temperature, right? Because temperature is the thing that is bonding together or balancing energy and entropy of the system. And he basically derived that if you combine quantum field theory with general relativity, you can derive temperature of a black hole. It's not a complete merger, like he didn't use quantum gravity to do it, but he took quantum field theory and placed it inside a fixed but curved space-time. And what he basically shown is that if you have a vacuum around a black hole, that from a point of view of a distant observer, the black hole seems to be radiating particles as a black body of a temperature, which is this. So the important idea is that due to the curvature of the space-time produced by the black hole, different observers don't agree on the vacuum state of the field theory. And as a result, from a point of view of a distant observer, there is a radiation, so-called Hawking radiation, coming from the black hole. The weird thing about Hawking radiation, among other things, is that it's inversely proportional to the energy or to the mass of the black hole. So when the black hole is very large, it's radiating only a little. But as it decreases, it's like heating up. Which is weird because usually when you have very energetic system, it's radiating a lot. And as it is cooling down, the temperature is coming down as well. And the radiation is slowing down or being mild. But in the case of black holes, it's the other way around. When the black hole is very large, that means massive, and that means energetic. It's radiating only a little, so little that it's basically undetectable on astronomical scales. But when the black hole starts being very, very small, then the temperature of the radiation goes up and basically even maybe hit infinite temperatures or asymptote to them. Now, there is a different way how to interpret Hawking radiation, which Hawking didn't like, but then Frank Wilczek basically put it on a solid ground, and Frank Wilczek got a Nobel Prize, so we should take him seriously. And the idea is, well, you can think of the process of radiation as like formation of virtual pairs. And sometimes this formation takes place very close to the horizon, and one half is captured with negative energy, and the other one is radiated away. So you can think about it this way. Now again, as I said, Hawking temperature doesn't seem to be testable, or at least to be detectable by observation, because for astronomical black holes, the temperature is just too low. But it has been recognized that basically Hawking temperature is, or Hawking radiation is basically the same thing as is something called Unruh radiation. Unruh radiation is a temperature felt by a particle that is accelerated. So if something that is accelerated with respect to something that it, instead of seeing the vacuum state, it sees a thermal state with a temperature T. And people are trying to measure in real labs the Unruh radiation, and if the Unruh radiation will be confirmed experimentally, then we can probably believe that the Hawking temperature is real as well. So far this has only been proven theoretically, but maybe we'll get some proofs shortly. Now, Hawking temperature poses some important questions. So for example, what happens to the information? You throw something into a black hole, you increase its entropy, and then the black hole is losing mass by radiating thermal radiation that carries no information. So there was a lot of information in the black hole that you didn't have access to, and then the black hole can evaporate, and suddenly then it's gone, and you don't know what happened to it. Now, some people claim to have resolved this paradox. I haven't followed this line of research, but recently a group announced that they've been able to resolve the information paradox. So the jury is still out, I would say. And the other question that is more relevant to me is that if the infinite temperatures are avoided, because basically the temperature is 1 over the mass. So when the black hole becomes very, very small, the temperature goes up, and as m goes to 0, then the temperature goes to infinity. And basically the idea is that when the temperature is on the order of Planck's temperature, you would expect some effects to intervene and basically stop the evaporation process or do something with the temperature to prevent it from reaching infinite values. And also the question is, how does the evaporation happen? And as I said during the morning lecture, there are efforts to explain this using matrix models, like how does the evaporation actually happen. Now, this finding of Jacob Bekenstein and Stephen Hawking basically jump-started various areas of research. The first one is basically something that has been fathered by Leonard Susskind and his idea that the universe is a hologram, but not in the usual sense. Basically, this is just a catchy title for a theory that tries to figure out whether the dynamics of the universe cannot be described by a dynamics that happen on a boundary of the universe. And it wasn't very clear what actually even is a boundary in the universe, because it seems that we are living in a de Sitter space and we don't have a boundary, we have a cosmological horizon. But a couple of months ago, Susskind published a new paper how to define this correctly in a de Sitter space. So this is one of the area of research, like trying to figure out whether the dynamics governing our universe cannot be described equivalently by dynamics on the something called holographic screen, something that is around. Now, why would we even think this is possible? This is because, well, black hole is the densest object in the universe. and it can be described by some amount of information that is proportional to the surface area. That means if you have something less dense than a black hole, it also can be described by an information that is storable on the surface of this thing. So for example, if you take Earth, then the number of information on Earth and inside Earth can be stored on the surface of the Earth. And well, the trick is basically each bit of information can be stored in one Planck's area, which is very, very small. It's 10 to the minus 70 meters square. So there's plenty of information, obviously, but he's trying to basically enlarge this idea for an entire universe. Now, during the first lecture, I mentioned that some people are trying to figure out like whether it, meaning the universe and everything, can be derived from bit or qubit, which is basically some type of information content or information dynamics. And well, this is also closely related to this. It's showing us that the idea of entropy and information seems to be important even on the most fundamental scales. Now there is another line of research that is related to this idea of entropy of black holes, which is Verlinde's theory of gravity. What he did 10 or 11 years ago is basically he took the area law, the relation between the entropy and the surface of a black hole, and he used it to derive Newton's law of gravity. And not only that, also in a certain sense, also Einstein field equations. Now, for some, this isn't so amazing because, well, basically, Jacobson in 1995 used Unruh radiation to derive Einstein field equations, so it seems to be working both ways. But then recently, and I think it was 2016, Verlinde wrote another interesting paper when he basically combined the area law for black holes with a volume law that holds for dark energy. And he basically showed that the dark energy and dark matter can be a result of the same phenomenon. And not only that, actually, his predictions are matching observations rather nicely. So he was able to produce a curve that is connecting, what was it? It was the radial acceleration in galaxies with observed radial acceleration. And there is just some law, and basically his prediction matched the data perfectly, same way as Mond, which is modification of Newton dynamics, and probably even better than just, well, ordinary theory of gravity. So maybe there is something to it. It's called entropic theory of gravity. And it's probably not perfect so far, but it's worth looking into. So these two papers, Hawkins and Bekenstein, started different areas of research. Okay, so now let me return back to the black holes. Two open questions are whether is the singularity indeed singular, and whether is the temperature divergent. So if there is something that prevents the temperatures to going to infinite values, or it just stops somewhere. And something I did during my research is that basically ask myself the question whether the Planck scale physics can change this picture somehow. After doing the research, I realized I wasn't the first one, that there were other people working on the same subject. But basically the idea is that let us take a matter distribution that isn't singular, but it's something very similar to a delta function. So this is the Planck's length, constant lambda, and you have e to the minus r over lambda to some power alpha. In my case, alpha was equal to 1. In cases widely used in the literature, alpha equals 2, and there are some examples with other values of alpha. And basically the matter distribution looks like this. It's non-zero at the beginning, and then it drops very, very sharply. And a couple of Planck's length outside of the origin is basically close to 0. So it's not singular, but it's very, very close to it. So the thing you can do is with this is that basically you can take this type of matter distribution instead of the singular one, and then plug it into Einstein field equations and find a solution. The solution to Einstein field equation in this case is basically the factor g/tt, which tells you about the slowing down of the clocks. So very far away from the origin, it's -1, as in the ordinary case, which is shown using the red line here. So we are a couple of Planck's length away from the singularity. Everything seems as before. Nothing special is happening there. Now the red line is the usual Schwarzschild black hole, and you can see that it crosses zero value only once. So this is the value equal to 0, and this marks the position of the horizon. Now in the case of having non-singular matter density, so for example those exponentials, then the solution looks like this. You have two horizons. One is close to the origin, and the second one is somewhere out there. So suddenly you have black hole with two horizons, a very, very small one, and then one that is very close to the Schwarzschild value, but deviates from it for very small black holes. The second thing you can do is basically compute the temperature of the black hole. The temperature of the black hole, as derived by Hawking, is proportional to the surface gravity at the horizon. So it's basically defined by steepness of this curve at the point where it is crossing the horizon. So this one is sharp. That means the temperature of this black hole is larger than this black hole with a fixed mass. So for all of the cases, you can compute what is the temperature of the black hole with respect to its mass. Again, the red curve is the classical Schwarzschild result, and it goes as 1 over m. So when m, the mass is very large, it's small, and as m is decreased, the temperature goes to infinity. So this is the classical result. And it was known that in all of the three considered cases, alpha equals 1 to 3, the scenario looks different. It's basically the temperature is going up, and then very suddenly, instead of going to infinity, the temperature very sharply drops to 0. Now I'm using rescaled values. So basically I have rescaled m and t to be, I have rescaled the plots with respect to the maximum temperature reached. So now it's 1 in each of the cases, and to the minimal mass they can have, so they converge here. And you can see that in all three of the cases, basically the temperature versus mass curves is the same. It goes up, follows the Schwarzschild black hole, and then very, very sharply drops to 0. So first, the important lesson is that structure of a space on a Planck scale change the behavior of black holes. So the structure of space made the singularity non-singular. So it's called a regular singularity, which is like an oxymoron, but in this sense. And it affects the behavior of the black hole. Instead of reaching infinite temperatures, the temperature goes to 0. It gets close to the Planck's temperature. It ends up like 2 orders below it, and then it's basically frozen. And it has been conjectured a couple of years ago that such microscopic black holes, which have been frozen, are a very good dark matter candidate. This is because first, they are very small. Their cross-section is on the order of 10 to the minus 70 meters squared. So they are impossible to interact with. Also, they are quite massive, like their mass is on the order of 10 to the minus 8 kilograms. That's basically the Planck's mass from the first lecture. So they are quite massive, and there doesn't have to be a huge number of them. So maybe basically one microscopic Planck size black hole for every cube of, I think it was 1,000 kilometers or something like that inside the universe. Maybe even way less. I don't remember the exact value. So it's quite interesting. Now, 2 more surprising results is, the first one is Hawking radiation recoil. Something I didn't know a year ago is that when 2 black holes merge, they can merge in a way that will produce gravitational waves with a very large momentum heading in one direction. That means that the resulting black hole will get a recoil kick and can be basically moving very fast the other way around. So I tried to find out whether there is some kind of Hawking radiation recoil. And again, as I realized, some people were thinking about this before in a different context. And what I found out is that during this last stage of the evaporation, something funny happens. Basically, the radiation is so energetic that from this maximal temperature to 0 temperature, the black hole gets, by evaporating, between 10 and 100 quanta of radiation. So it's radiating very energetic particles in random directions, but only a very small number of them. So that means that radiating every particle is like a step in a phase space. So this is like a drunken sailor doing random steps in a momentum space. And after doing 10 steps, the average distance from the beginning is 1 over square root of 10. And because the number 1 over square root of n is very small, then the resulting Hawking radiation recoil is very large. I have calculated that in the considered cases, the black holes obtains velocities that are up to 10% of speed of light, which is weird because some people believed that microscopic black holes should be a dark matter candidate, which should be cold dark matter, which means slow. Now, to understand how could they have been formed very fast, but are slow now, you have to consider when they could have been formed. There are 2 possible scenarios for formation of microscope or of primordial black holes. Primordial black holes are basically black holes formed during the earliest stages of the universe. So not black holes that form as a result of supernova, not supermassive black holes inside the active galactic nuclei, just black holes from the beginning of the universe. There were 2 relevant stages. The first one is the inflation era, which we don't know much about, but trying to figure out, which is like the first moments of the universe when it was expanding rapidly and we have basically no clue what was going on. There are many ideas, but nothing very conclusive so far. And then when the inflation era was over, the universe began something called radiation-dominated era, when physics that we believe we do understand took place, something like formation of baryons and things like that. And during the radiation-dominated era, which lasted like 50,000 years, the universe was still very hot. So people calculated that if you have some form of spontaneous overdensity in the medium, whether it can form a black hole. And the result was that yes, when the universe was dense enough, black holes in principle could have been produced. And then they derived some kind of a law between the time of the formation and the mass of a black hole. In the inflation era, like the options are, there are numerous options how primordial black holes could have been formed, because there is a lot of exotic physics under consideration describing this inflation era, like collapses of cosmic strings and domain walls and bubble collisions. And many of them can produce primordial black holes. Now, if the structure of space really has some structure on Planck scale, it means that Hawking radiation has a large recoil effect on microscopic black holes. And for them to be consistent with the cold dark matter model, they need to have been able to slow down considerably. And I have done the calculation, and it seems that they cannot be formed during the radiation-dominated era. So the most plausible explanation at the moment is that they were formed during the inflation era. And again, like the details I gave you were very sketchy, but the bottom idea is that, again, like Planck scale physics seems to be important for understanding present-day cosmology. Like understanding, for example, what is the origin of a dark matter is closely related to the structure of space on a Planck scale. It still can be true that dark matter isn't composed of microscopic black holes, but still to maybe even like exclude this candidate for dark matter, you need to understand also Planck scale physics, which is, well, surprising. Okay, so let me wrap it up. We expect from looking at the Planck units that something has to be happening on scale that cannot be accessed by particle accelerators or super microscopes or any other means available to us so far. So we expect that there is a lot of unknown physics that in principle we could study, but don't have the tools at the moment. We are searching, probably since Einstein, for a theory that would be connecting quantum theory with gravity. And sometimes people call it like the theory of everything, because gravity and quantum theory is everything we know so far. So if we were able to merge them, that it would be the theory of everything. But some of the results that I've shown you hopefully convey the message that it seems to be at least plausible that there is a lot of from physics that we actually have no idea that is going on in there. That between I don't know, Large Hadron Collider energy scales and Planck energy scales, it's not just about adding new particles to the mix, but changing the rules of the game considerably. So for example, something like the area law of a black hole something you cannot understand by just adding new particles to the standard model. So we expect that not only like emergence of new particles, but perhaps of new physical principles while moving towards this new scale. And when, for example, there is a news that maybe we have discovered new particle or there is some kind of anomaly, that at least for me, it's not interesting because of the particle itself, but because each of the particles we know so far brings in some new kind of interesting physics. And not only physics, but like a different set of principles. And if we get to observe a new particle, it will be mostly interesting for me, like in the way it affects the rest of the physics, not just the particle itself, but the way it enters the picture. And the surprising result for me, it's worth at least thinking about possible experimental or observational test of quantum gravity. So for example, if there would be a large number of small black holes, we can think about detecting the Hawking radiation from them. And actually this has been done before. People are trying to see gamma ray bursts from the microscopic black holes, but at least I do believe now that if the dark matter is consisting of black holes, that the black holes are very small and have ceased the evaporation process a long time ago, but still it's a sign that it's worth thinking about whether we can see some effects of that is stemming from quantum theories of gravity. And also people, I hope right now, are working on experimental tests of quantum gravity, for example, in the sense that forgot the name right now, but yeah, the Cavendish experiment that we used to measure the gravitational constant and then also the mass of the Earth and mass of the Sun and etc. So what Cavendish did was he measured the attractive force between two weights he used in his laboratory, and the gravitational force is very weak, but still with precise enough experiment he was able to measure the force it produced and therefore measure the Earth or measure the mass of the Earth as well. Now people are trying to do the same thing, but again shifted a couple of gears up with quantum effects. So basically take very small particles, let them interact gravitationally and see if you can see how quantum meets the gravity. So maybe I don't want to call it like doing a two-slit experiment, but something of this kind, like two-slit experiment and there will be a massive particle sitting close to one of the slits or something more sophisticated, but of this kind, like measuring gravitational effects of quantum particles, which also should give us some clues about how to merge those two huge theories together. So I believe this is everything from my side. Thank you for your attention and please feel free to ask. Ask any question you like.
So please, if there are any questions or comments. I have a question. So, where do you think is going to be the first place that people experimentally detect signs of Planck scale physics, and when is it going to be?
It's a difficult question because what you can do is like the tabletop experiments in laboratory, but those won't be probing, I think, Planck scale physics. They're just probing combination of quantum with gravity. And like my hope is that the best source of particles that are at least close to the Planck scale is the universe. We are sometimes bombarded by particles with energies of 10 to the 20 or 21 electron volts, which is like way more than what we see from what we have in the particle colliders, but it's just only a couple of those every year. But maybe this can be the way to go, like trying to get those high energetic particles from the universe, and then maybe they can get close enough to the Planck scale. So maybe something like this, and people are already working on this. So this might be our best chance that there is some kind of particle accelerator somewhere in the universe that is producing particles that are close to the Planck's energy scale. But it's tricky because at least for example, for protons, there is a speed limit, because as they approach energies around 10 to the 20 electron volts, they are so quick that they are seeing the cosmic microwave background as being, I think, very hot, and they are interacting with it. And there is some decay of those highly energetic protons. So maybe even the universe is producing Planck's or close to Planck scale particles, but it's just also preventing us from seeing them.
So somehow everybody is happy about your lectures, and there seem to be no more questions or comments. So thank you very much for this nice series,
Thank you.
for making it very understandable, and well, we are looking forward to meet together next year at the next summer school, when hopefully COVID restrictions will be over.
Yeah, hopefully during 6th wave.
Okay. So thank you and goodbye.
So if you have any more questions, feel free to email me or drop by at the office during the semester, and we can chat about this more. Goodbye.
Bye-bye.